Hi everyone, I am Sishun Huang and I am from National Kaohsiung University of Science and Technology, Taiwan. Today, we are going to talk about GANs, which stands for Generative Adversarial Networks. GANs are a framework used to learn generative models. The outline of today's presentation is as follows. First, the introduction explains what GANs are and the basic idea behind them. Next, the GAN components looks at the architecture of the two main parts of a GAN, the discriminator and the generator. Finally, the adversarial training covers the definition of loss function, the max-min problem formulation, and the training algorithm for both the discriminator and the generator. What are GANs? GANs are a framework for estimating generative models through an adversarial process. The three letters G, A, and N stand for generative model, adversarial process, and the neural networks respectively. The generative model is a model that generates new data similar to the data it was trained on. The adversarial process refers to training the generative model by having it compete against a discriminative model. Finally, neural networks mean that both the generative and the discriminative models are implemented using neural networks. Let's take Minister dataset as an example. We use the Minister dataset to train a generative model called the generator that learns to generate handwritten digits from 0 to 9. Here, you can see some real digit images from the Minister dataset. The idea is that we start with a random noise, and the objective of the GANs is to train a generator so that it can turn this noise into digit images that look like real Minister images. To make this work, we introduce another model called the discriminator and train the generator through the adversarial process, where these two models compete with each other. In GANs framework, both generator and the discriminator are implemented using neural networks. The main concept of GANs is to train generator that maximize the chance that the discriminator makes a mistake. At the beginning of training, the generator produces fake images that look very different from real images. In this situation, the discriminator after training can easily distinguish real images from fake ones, resulting in almost zero error. As a result, the generator is encouraged to produce better images in order to increase the discriminator's error rate. After some training, the generator starts to produce better images that can fool the discriminator. In this case, even after training, the discriminator has an error rate of about 16%. Motivated to push this error rate even higher, the generator continues to improve and generate images that look more and more like real ones. Eventually, the images generated by the generator become nearly indistinguishable from the real images. As a result, the discriminator is no longer able to tell them apart, and the discriminator's error rate reaches 50%. In the GANs framework, There are basically two main parts, the generator and the discriminator. The generator can be thought of as a model that tries to draw images. It is usually made up of several deconvolution layers. Given a noise Z, the generator pushes it through those deconvolution layers to finally produce a fake image. The discriminator is basically the judge in the game's framework. It is usually a convolutional neural network for binary classification. That is, distinguish real images from fake ones. When you give an image S, the discriminator runs the image through a bunch of convolution layers to obtain a feature map. Then it flattens the feature map into a 1D feature vector. And finally use the fully connected layers to output a value Y, which represents the probability that S is the real image. Obviously, 1 minus Y means the probability that X is a fake image. For a real image where Y hat is 1, we want the discriminator to output Y equal to 1.0, which means 1 minus Y is 0. For a fake image, we expect Y is 0, and that takes 1 minus Y is 1.0. After introducing the architectures of the discriminator and the generator models, we now move on to explain how they are trained. The loss function L of GD defined to train games is just the binary cross entropy LVCE computed over all training samples from real image set S1 and the fake image set S0. Here, Y hat denotes the ground truth label, and Y is the predicted real probability. For a real image X in S1, the discriminator's output probability Y can be written as D of X. The cross entropy of this real image is therefore minus log of D of X. For a fake image X in S0, its probability output from the discriminator is 1 minus D of X. Similarly, the cross entropy for this fake image is minus log of 1 minus D of X. Since the fake image X is generated by the generator using a noise vector Z as input, we can write it as G of Z. So in this equation, the term X can be replaced with G of Z, and the set S0 corresponds to a set of noise vectors Z sampled from the noise distribution. Accordingly, the loss function L of GD can be rewritten in this formulation. The binary cross entropy for a real image becomes minus log of D of X, while the one for a fake image becomes minus log of 1 minus D of G of Z. In the game's framework, training the discriminator means to decrease the classification error by minimizing the loss L of GD. On the other hand, training the generator is all about to fool the discriminator into misclassification, which it does by maximizing the same loss L of GD. By putting these two objectives together, we get the classic max-min optimization used to train the generator and the discriminator. When we further expand L of GD, we can arrive at the full max-min formulation. The algorithm to train the generator and the discriminator works in an alternating manner. First, we keep the generator G fixed and update the discriminator to get optimal discriminator D start. Since G is treated as a constant in this step, its influence can be ignored in the loss function L of GD. This leaves us with the objective function used specifically for training the discriminator. Next, after updating the discriminator, we fix D and update the generator G. In this step, D is treated as a constant. We can ignore its influence in the loss function L of GD, leaving us with the objective function for training the generator. Because D is a constant in this formulation, the loss term defined over real images is also a constant and can be dropped. In the end, we obtain the final objective function used to train the generator. Here, we give an overview of the training algorithm used to estimate G star and D star in an alternating manner. At the beginning, the generator and the discriminator models are initialized as G0 and D0 respectively. We then fix G0 and use the discriminator objective function to update D from D0 to D1. Next, we fix D1 and use the generator objective function to update G from G0 to G1. By repeating these steps for several iterations, we eventually obtain the optimal models G star and D star. After giving an overview of the training algorithm, we now go into more detail about how G and D are updated respectively. To update D, we firstly sample a mini batch of M real images X from dataset, and a mini batch of M noise samples Z from noise distribution. We then use the generator G to produce fake images G of Z from Z. Then, we use the discriminator D to classify the real images and compute layer overall loss. Similarly, D is used to classify the fake images generated by G and compute layer overall loss. Finally, we add these two losses together to update the discriminator D while keeping G fixed. To update the generator G, we only sample a mini batch of M noise samples Z and use G to generate fake images G of Z. We then use D to classify the fake images G of Z1, G of Z2 to G of Zm, and compute their overall loss. Finally, we use this loss to update the generator G while keeping D fixed. In this lecture, we have covered the GAMES framework for learning a generative model in an adversarial manner. I hope you enjoyed the video. Thanks for your listening and have a nice day.